Hello class, this topic is on basic functions and transformations. We will begin by reviewing these 6 nonlinear functions, and then we'll discuss how to transform them by stretching them, shifting them, and or reflecting them across either axis. Let's begin with the function y equals x squared. If you're not already familiar with this function, you can make a table of points by picking various x coordinates, squaring them, and calculating the corresponding y coordinate. For example, if x is 0, you square that and you get y equals 0, so 1 point should be the origin. If x is 1, square it, you get 1, so 1, 1 should be a point. If you plug in 2 for x, you should calculate 4 for y. You can even plug in numbers like 1/2 for x and square that and get 1/4. If you plug in a negative number, like -1 and then squared becomes +1, -2 and then square that, you get +4. And in the end, you have what's called a parabola with vertex at the origin. Now let's shift over to the next function. Y equals square root of x. If you try to evaluate this function at x equals 0, you get 0 back, because the square root of 0 is 0. The square root of 1 is 1. The square root of 2, if you reach for a calculator, you'll get about 1.4. Square root of 3 is about 1.7, and square root of 4 is 2. You cannot plug in negative numbers into this function without getting imaginary numbers. So no negative inputs are allowed, so just 0 and higher. And then what really winds up happening here is you get the graph of a sideways parabola. The top half of it, that is. The bottom half, not present. Let's go to the next function. This is y equals absolute value of x. The absolute value of a number is the distance that number is from 0 on the number line. So the absolute value of 3 would be 3, and the absolute value of -3 would also be 3, because both 3 and -3 are 3 units away from 0 on a number line. Basically, in effect, the absolute value of a number gives the positive version of that number. So the absolute value of 0 would still be 0. 0 is the only non-positive, non-negative number. The absolute value of 1 is 1. Absolute value of 2 is 2. Absolute value of 3 is 3, etc. The absolute value of -1 is +1. The absolute value of -2 is +2. Absolute value of -3 is +3, etc. You get 2 portions of linear functions put together, making this V shape. Now let's go to the next function. Y equals x cubed. Just cube the inputs. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, which would be off my scale here, out of my window. -1 cubed is -1. Remember, if you cube a negative number, it stays negative. -2 cubed would be -8, off of my scale. And this graph winds up looking like the following. Let's go to the next function. Y equals cube root of x. So now we're going to cube root all of the inputs. The cube root of 0 is 0. Remember, when you cube root something, you're trying to find a number that, when cubed, gives you the radicand. The radicand being what's inside the radical. So the cube root of, say, a number like 8 would be 2, because 2 is the number that, when cubed, gives you 8. So the cube root of 1 is 1, because 1 cubed is 1. And in order to get a result of 2 here, I need to input an 8, but that's off of my scale. The cube root of -1 is -1. And the cube root of -8 would be -2, but that's off my scale. And we get what's kind of like a sideways version, if you will, of the function we just analyzed over here, x cubed. And finally, the last nonlinear basic function you should be comfortable with is called the reciprocal function. Y equals 1 over x. So that's the reciprocal of x. So whatever input you give, you do its reciprocal. So let's pick an easy input like 1. The reciprocal of 1 is 1. The reciprocal of 2 is 1/2. The reciprocal of 3 is 1/3. The reciprocal of 4 is 1/4, etc. And try inputting some fractions close to 0, like let x be 1/2. So 1 over 1/2 is the same thing as 1 times 2 over 1, which gives you 2. Basically, whatever x you input, when you do 1 divided by x, the end result is going to be the reciprocal of the input. And so 1/2 becomes 2 over 1, which is just 2. So if x is 1/2, y will be 2. If x is 1/3, y will be 3. If x is 1/4, y will be 1/4. And you get this curve that's in the first quadrant that follows the x and y axes like an asymptote. You could do similar with negative numbers, and you're going to get a -1 reciprocal is -1, -2 reciprocal is -1/2, -3 reciprocal is -1/3, etc. -1/2 reciprocal is -2. So in other words, when x is -1/2, y is -2, etc. And you get this mirror image piece over here in the third quadrant. Now overall, this is a function of x because it does pass the vertical line test. And 0 is the only number you can't do the reciprocal of. To explore these functions even more, I recommend you go to Desmos and type all 6 of them in and zoom out and zoom in and get a sense for what these functions look like with a little bit more accuracy. Moving on to the next page. Okay, we're going to summarize all the different ways that we to transform a function. Let's begin with if you want to shift a graph up k units, then what you need to do to adjust the rules, you need to add k to the rule. In function notation, looks like this. So f of x represents the rule, and then you add k after the fact. So as an example, let's apply this to x squared. If I want to move x squared up k, it would look like x squared plus k. And we're assuming k is some positive number, by the way. Let's just go ahead and assume k is positive in this whole table. If you want to shift a graph down k units, then you subtract k from the rule. So it'd be the rule of the function and then minus k. So in the case of x squared, it'd be x squared minus some positive number, would shift the graph down. If you want to shift the graph right k units, then we need to do a function evaluation at x minus k. In other words, replace all the x's in the rule, all of them. If there's a bunch of x's in the rule, then you need to replace all of them, not just some of them, with x minus k, which in function notation looks like this. You do f of parentheses x minus k end parentheses. That means you plug x minus k into the function. So the function rule here is x squared. I'm going to take x squared. I'm going to replace the x with x minus k, which use parentheses when you do this. So the x is gone. I've created a vacant spot where the x used to be, and I'm going to plug in x minus k there instead. If you want to shift a graph left, then you do the same thing, but you replace all the x's in the rule with x plus k's. Function notation looks like this. You do f of x plus k, and applying it to the rule of x squared, it would look like x plus k, all in parentheses, and then the square. So the vertical shifting is the k is outside the rule of the function, and horizontal stretch or shifting, you're going to, the plus minus k is where the x, you have an x minus k or an x plus k where the x used to be in the parent graph. And in the case of x squared, it looks like it's just inside this, it's before you do the squaring, it's inside with the x. If you want to stretch compress vertically by a factor of k, now if k is more than 1, if this k here is more than 1, then we'll get the stretching. If k is less than 1, we'll get the compression for vertical. We just multiply the rule by k. So it looks like this in function notation. You do k times the rule. So if I want to stretch or compress x squared by a factor of k, then I just do kx squared. And again, if this k is more than 1, then x squared will be stretched vertically. If k is less than 1, x squared will be compressed vertically. Now, if you want to stretch compress horizontally by a factor of, notice I'm doing the reciprocal of k this time, then you replace all the x's in the rule with kx. So replace all the x's with kx will be a compression by 1/8 or stretching by 1/8, depending on what k is. Because k is general here, k might be a fraction to begin with. So if this k right here is a half, then 1 over a half, this will be a 2, and this will become a stretch. But if this k is more than 1, like 3, then 1 over a k will be a third, and that's going to correspond to a compression. And what this looks like in this case is, here's x squared, you replace x, get rid of it, put parentheses, replace it with kx. So if the k is in with the x before you do the square, that's unlike this one up here, then we are talking about a horizontal compression and or stretching depending on what k is. If you want to reflect a graph across the x-axis, you just multiply the rule by -1. So you do the opposite of the rule. So in this case here, you would do the opposite of x squared. Remember what I said about order of operations here. You would square the x and then do the minus. And if you want to reflect a graph across the y-axis, you replace all the x's in the rule with -x. So if we used to have x squared, replace that with negative x, and this is what it would look like. Of course, in this case, the negative will be canceled by the square, and it'll go back to x squared. That's just simply because x squared, if you take that graph, which is already symmetric across the y-axis, and then you reflect it across the y-axis, it won't be any different. In other words, every even function, this tweak doesn't change it if the graph is even to begin with. If it's already symmetric across the y-axis, then replacing all the x's with negative x will not have an effect. Okay, and so there's our summary of all the different transformations you will be responsible for knowing. Now let's put some of them to practice. Here we have some functions on the same grid. Plot the indicated transformation. Okay, so this function that's provided is the f of x, right? And our goal is to plot what f of x plus 2 would look like. So this corresponds to the vertical shift. So the key points, I'm going to move everything up 2 units from where it used to be. I'm just going everything up 2 units, everything up 2 units, and then drawing the rest of it. So there's our new graph. Okay. This next one, if I do f of x minus 3, notice the minus 3 is in with the x. This is where you replace x with x minus 3. That's going to be a shift. Let's refer to our table. If you replace all the x's with x minus 3's, then we are going to the right 3 units. So this entire graph needs to go right 3 units. So this point right there needs to go right 3 units. In fact, let me write it down. We're going to go right 3. Up here, this was a up 2 situation. Right 3. So I'm going to start with that point there, move it right 3. It's actually going to fill in perfectly where that gap is. Move this point right 3. It's going to be there. And then the v. I'm going to make this a different color than the original so that we can see that it's in fact. Okay, so the black graph was moved to the right 3 and it makes the red graph. In fact, why don't we do all of the new graphs red, which is different than we did up here, right? Up here, the parent was red and the new graph is black, so don't let that throw you off. Here, the black graph is the parent and the red graph is the new one. Okay, when you do put a negative sign in front of the function, negate the rule of the function, this will be reflect across the x-axis. So every single point, let's focus on that one first, is now this exact same distance but on the opposite side of the x-axis. Right, so we're going to get this portion there. Our v is going to go up this time, crossing the x-axis at the same location as the other one crossed the x-axis, and we get this result. Let me go ahead and make that red again. So there's our reflection across the x-axis. When you do f of negative x, this is where we reflect across the y-axis. So focus on that point, reflect it to the other side of the y-axis. So we'll get that portion, and our v will be here and end there. So you can reflect the black graph across the y-axis, and we get the red graph. Okay, we'll practice 4 more of these. If you double a function, this is the case of the vertical stretch. So every point will be twice as far from the x-axis as they used to be. This point here will now be right there. So we're still going to get a horizontal segment there. It looks like we're just doing a vertical shift by 1, but we're doing a vertical stretching. Any x-intercept is going to stay the same. So that's still going to hit there. This point here will be twice as far from the x-axis as it is now, so it's going to be down to -2. And then let's go ahead and complete this. Okay, so here's the result of doing a vertical stretch by a factor of 2. Every point is now twice as far from the x-axis. X-intercepts do not move when you do vertical stretching or compression. Right? Those are going to be in the same spot as they were before, because when you double 0, you stay 0. Every other point will be twice as far from the x-axis as it used to be. Here's a vertical compression by a factor of 1/2. So this point here will be right there. Let me write this down as well. I forgot I should be doing this. Multiplying by 2 is a vertical stretch by 2. Multiply by 1/2 is I'm calling this a vertical compression, is the word I use for this case, by 1/2. So every point in my new graph will be 1/2 as far from the x-axis as it used to be. So we're going to get a horizontal portion right there. The intercepts will not change. This bottom of the v will be 1/2 as far away. The hollow point will be half as far away. The intercept will not change. And we'll get this shape. F of 2x. Right? Because the 2x is in the parentheses, we are talking about a horizontal, either compression or stretching by a reciprocal of that number there. So instead of 2, it's by a half. So that means we're going to actually do a compression. So this is a horizontal compression by 1/2. Okay, so every point is going to be half as far from the y-axis as it used to be. So the hollow point will be here. The bottom of the V will be there. Make that better. There we go, there. Any point on the y-axis is not going anywhere because it's already on the y-axis, so cutting its distance to the y-axis in half doesn't do anything. But the terminal point, that point right there, will no longer be there. It'll be half as far. So our graph's going to end right there. And so we're going to have a horizontal part right there that's only half as long. And we'll have a skinnier V that ends right there. And here is our horizontal compression by a factor of a half. This is an obvious case where a horizontal compression is not the same thing as a vertical stretching. It is obvious that compressing horizontally is not equivalent to stretching vertically in this case. Stretching vertically looked very different than compressing horizontally. And then this last one here, we have another horizontal compression / stretch. The K is a half right there, so do the reciprocal of K, that gives you 2. That tells me this should be a stretch. Because it's more, the reciprocal of K is more than 1, so we're stretching. This is a horizontal stretch by a factor of 2. So we're going to be doubling all of our horizontal distances from the y-axis. Let's start with this hollow point right there. It's going to be twice as far from the y-axis, right? Go twice as far from the y-axis. Let's go down to this corner right there. It's going to be twice as far from the y-axis, so double this length to there. So there's going to be the tip of my V, twice as far from the y-axis. The intercepts move. I should have pointed that out in the last one, but this intercept looks like it's at 1.5. Well, that intercept is now going to be at double that, at 3. This intercept looks like it's at 1/2. We'll double that. The point on the y-axis will not go anywhere. But this point here will be twice as far from the y-axis, so it's going to be all the way out to here. And so our end result is it's going to be a shared portion there, the horizontal. Notice when you compare stretching in vertically versus horizontally that the height of the peaks and valleys, like look at this right here, the height of that sharp corner was exaggerated, it was pulled down. Right? In the case of the compression, it was corner here got closer to the x-axis, over here it got further, right, from the x-axis. But when you do horizontal stretching compressions, the heights do not change, right? It was still at -1 height. It moved horizontally. The peak moved horizontally, not vertically. Same thing here. The peak is at the same height. They're both at -1, the y-coordinate, but it's the horizontal position of the peak that's been moved. So some very important observations to make about vertical stretching versus horizontal stretching and or compression. Okay, a couple more slides here. We're going to begin with the parent graph of x squared. And the purpose of this slide is to show you that the order in which you do multiple transformations can have effect on the final result. So if you want to shift up to and reflect across the x-axis, the order in which you do that is going to produce different things. For example, let's do the shift up to first. So move everything up to. We're going to have a parabola in here like this. And then reflect across the x-axis. Well, the x-axis is down here. And I'm reflecting this one, not the parent. So reflect after you've done the shift up. And if you take the shifted up parabola and then reflect that across the x-axis, you're going to wind up with this result. I'll just say that this is the final result. Step 1 and step 2. So maybe we could label them by steps. After doing step 1, maybe I'll color code these. So this was, we'll just put a 1 there. That was step 1. And then after doing step 2, our final graph was down here. So 1, 2 steps. If I start with x squared and I do the reverse order, same transformations, but just in reverse order. If we first reflect across the x-axis, so step 1 would put us put our parabola down here like this. This would be step 1. And then take that orange one and shift it up 2. So when I go in this order, after doing the second step, compare the two reds. They're not in the same place at all. So the order in which we did these transformations was significant. Now in the first case, let's go ahead and show you what the rules would be for each color along the way. So if I started with x squared and I shifted up 2 first, then this orange one is x squared and then plus 2. That is the rule for the orange. I'm going to get rid of these steps numbers. I don't want that to be confusing. But if you want to reflect now the orange across the x-axis, then you need to negate the rule and make sure you negate the entire rule. So this one should be the negative of x squared plus 2. That's how you take x squared plus 2 as a rule and reflect it. You negate the entire thing. Don't make the mistake of just throwing a negative lazily in the front and write this. This is not the same thing as reflecting this across the x-axis. Over here, to get the orange, we started with x squared and we first reflected it. So negative x squared is what we did there. Then we took negative x squared and shifted it up 2. So the final graph here looked like this, negative x squared and then plus 2. So the two red graphs, here are their rules, and they are different, right? Negative x squared and then plus 2 is not the same thing as negative of x squared plus 2. In fact, what you can do with this first one here is distribute that negative and write it as negative x squared minus 2. And now you can see without parentheses why the red graph in the right picture doesn't have the same rule as the red graph in the left picture. That's why their graphs aren't the same. But notice what's currently circled is equivalent. I could have gotten to that red spot. I could have achieved this graph right here by doing the opposite of x squared first, which is what this orange one over here is, and then doing minus 2 after. So in other words, take this orange graph over here and shift it down 2, and it will become this red graph. Okay, now we're going to do some multiple transformations. Graph the following function by beginning with the appropriate parent function and graphing one transformation at a time, all on the same grid. Okay, let's start with the parent function, which is, hopefully you can recognize that there's an absolute value involved here, so I'm guessing that we're probably starting with the absolute value of x. So here's our parent function, and we're going to do one transformation at a time until we wind up with this statement. Now my recommendations are to, if there's anything inside the absolute value with it, is you can take care of that left-right motions first. Or you can do, if you recognize anything as a left-right shift or a vertical shift, do all the shifting last and first focus on any sort of reflections and or stretching compressions that might have happened. So in other words, I'm going to do the stretching first. I'll do all the shifting last. So what happens, let's do color code this. Let's go to orange next. What happens when you double a function? That corresponds to a vertical stretch by a factor of 2. So whatever y coordinate you used to have, double it. Right, so double 2 to 4, point there. Double 3 to 6, and it's going to be slightly off the graph, a point up there. So all the heights are now double what they used to be. 0, of course, doesn't double, or it doubles but stays 0. So we from 1 to 2 there, from 2 to 4 here, from 3 to 6 here, so that goes just off the graph. So we are doubling all the y coordinates, and we have an orange graph that's also a V, but a little more narrow of a V. And this was a vertical stretch that we were thinking. So let's write that down. Vertical stretch by a factor of 2. When I say factor of 2, it means by doubling. Factor means multiply by 2. So by factor of 2 is, if you just say by 2, if I say vertical shift by 2, then that just means everything went up 2 units. When I say vertical stretch by 2, that means we multiplied by 2. Right, so I'm being a little bit lazy here. I should probably write the word factor of 2, because the word factor of means multiply by 2. Okay, next. Let's worry about doing that negative, get that in place. Let's go green this time. And when you multiply a rule, and the rule we're multiplying is the orange one, we're going to multiply the orange by negative. And when you do that, you reflect about the x-axis. So take the orange and reflect it across the x-axis, and it's going to make with vertex at the origin still. All of these so far have a vertex at the origin, a sharp corner at the origin. Okay, now that we've gotten the reflections and or stretchings out of the way, now let's finish with the horizontal and vertical shifting. Let's do the horizontal first, and blue will be next. To go from green to blue, I erase the x and replace it with x plus 1. In other words, the plus 1's inside the absolute value. And when you replace x with x plus 1, then we have a shift left and then 1 unit in this case. So now we need to do a v that has been shifted left 1 unit. And as I'm doing my v, I'm being mindful to get the slopes right. Look at the orange was over 1 up 2. So the green should be over 1 down 2. And since the blue has just been shifted, then I expect the v to be over 1 down 2, over 1 down 2, etc. That's how I'm getting the steepness of the v accurate. Okay, or you could have done something like this, just kind of grab the green and shift it left 1 unit. Right? I'm trying to draw all of them at the same time, but it's that visual of going left 1 unit is that you wanted. Right, so the blue is where we're at now, and then we have only one more step to do. We got to do that plus 4. That's going to be our shift up 4 units. Let's make this one purple. So to go from blue to purple, the only change I made was adding that 4, and that's going to shift up 4 units. Okay, so I could just grab the blue and I could do that, copy it. Let's do this, copy, paste. All right, so here's the blue, go up 4 units. So it's going to go right up the sharp corners right there. Of course, now I want to make that purple. And there's our final graph, the purple graph. Now, these do go down forever, so I'm not drawing all of it in this window, but the pattern continues. The domain and range, I don't ask for it, but I could now. The purple graph goes left and right forever, so the domain is all real numbers. So D and then that bold R. You put 2 bars right there on that R. It stands for a bold R. It stands for all real numbers. But the range is limited. Right, the highest point on the purple graph is at height 4. And every height below that is achieved, because the graph goes down forever without bound. So the range is negative infinity up to 4 when all is said and done of the purple graph. And then finally we have graph the following function. One more transformation to do. This one has a bit of trickiness to it because of the presence of a 4. There's a coefficient of x and a plus 8 next to it, all inside the square root. Well, do you recognize that it's definitely the square root of x is our starting point? This is our parent, because there's a square root involved, so this is a pretty good safe guess. And square root of x, oops, did not draw that right. It should go through 0, 0, 1, 1, and 4, 2. So there's our parent. And the danger of this one is some students will focus on, they'll do I'm going to multiply by 4 next. And they'll recognize this correctly as, oh, this is just a horizontal compression by a factor of 1/4, which is correct. It's going to be a graph that looks like something like this. But then how do we go to the next phase? Then here's the danger of what a student might say, that now I'm going to put that plus 8 there and say, okay, well, that's a shift to the left 8 units. But the danger here is, in order to accomplish a shift left, let's read this carefully. To shift left k units, you replace all the x's in the rule with x plus k and use parentheses. When I just lazily throw a plus 8 after the x, then I haven't actually replaced x with x plus 8. Because if I were to replace x with x plus 8 to make the shift happen, then you would have to use parentheses and it would look like this. This corresponds to a shift left 8. But when you remove the parentheses, this would be a 32 here instead, which isn't what we want. We want it to, without parentheses, we want it to be an 8. So here's my advice. When you have an x plus or minus a number right away and there's a coefficient of x, be careful. This is a dangerous spot. I recommend you factor that 4 out and look at this as if it had parentheses. Now I can see what the actual shift is. It's a shift left 2. Okay, so we actually want to to go from the orange to the green, we want to replace x with x plus 2. So let's erase all that stuff. And when I do that, there's parentheses that happen when you do the replacing. There's an x plus 2 there now. So now we have a shift left 2 units. And then, of course, if you distribute the 4, it looks exactly like what we are aiming for. Square root of 4x plus 8, which is what we were after. So take the orange and shift everything left 2 units. So the start of the graph will be there. This used to be at a quarter comma 1. A quarter comma 1, shift left 2 will put us at negative 1 3/4 comma 1. This is 1, 2. Shift it left 2 will be at negative 1, 2. Really, in the end, we just have this curve, copy, paste, make it green. Shift left 2 units puts me right there. And I didn't ask for domain range, but let's go ahead and do it. You can clearly see that as far as x is concerned, the graph only starts at negative 2 and goes to the right. So we have a domain of negative 2 up to infinity. And then the range, we start at a height 0 and go only up from there. But 0 is the lowest y-coordinate, so the range is 0 to infinity. Now, the last thing I want to do on this is show you what I did here on this slide, but using Desmos. I'll show you another way to do this. Okay, let's start with our parent graph. And there it is, already graphed. And we wanted to do a horizontal compression by a factor of 4. So I could do square root of 4x, make sure the 4 is in there, and we get the horizontal compression by a factor of 4. If I do a horizontal line, you'll notice, and pick 2 points on this, that the red point is 1 unit away from the y-axis, and the purple one is a quarter of that. It's a quarter unit away. And if I change that y to a 2 and compare these points, right? The red point is 4 units away from the y-axis, and the purple one is a quarter of that. So we do have this horizontal compression by a factor of a quarter. And now I want to shift that to the left 2 units. And if I just write square root of 4x and then just put plus 8, you'll notice that it is in fact, let's make it a different color, it is in fact 2 units left of the purple graph. Even though it looks like the purple and green are getting closer and closer together, remember that's an optical illusion. Horizontally, if I put a horizontal line in here like y equals 2, horizontally, the purple and green are always 2 units apart, right? Park this anywhere and compare the purple and green. They're always 2 units apart horizontally. Now let me hide those and show you the other way of doing this that I was telling you about. We're going to call this function f of x and just use a little bit of function notation. Put the x in there. Okay, there we go. There's our parent function using function notation. I can get the horizontal compression now by just using the function notation for doing a horizontal compression by a factor of 4, which is by plugging in 4x into the function. And notice that gives me the exact same result as when I did that purple statement. And then to this, we want to replace the x with an x plus 2. And let me just use extra parentheses in there. So here comes the x plus 2. Change the x to x plus 2, but leave the 4 there. And we get that purple graph, which is our final answer here. Right? It's the same as that of this green graph. So you have some notational tools here using Desmos to do transformations, so you don't have to keep writing huge complicated things. For example, let's go with a little bit more of a complicated of a function here. I'm going to throw some trig in there. If you don't know what trig is, that's fine. I just made a sine wave, and to that I'm going to add a point to x. Just making up stuff here. Okay, so we get this sort of a, looks like a wave that is going upwards as we go. It, gradually works its way up. So here's a function. We call it f of x. If I want to take this function and shift it right 1 unit, then I say, okay, well now I just have to plot f of, and to go right 1 unit, I need to replace x with x minus 1. And the black graph is 1 unit to the right of the red graph. And you can play with things. You can put a c there instead, add a slider for c, and then play it. So now we just got a whole bunch of different left-right shifts of this wave. as C varies. We're just shifting the red one left and right more and more. Throw a square on that. Let's see how, maybe you can see it better here. So we're just doing left-right shifts of whatever the red graph was. And if you want to do up-down shifts, put a plus, a constant there at the end, and then let C vary, and you see we just get vertical shifts up and down. If you want to animate some vertical stretching, then put the C in front. And notice what's happening here. We're getting different vertical stretches and or reflections. There's a reflection at play here when C is -1. When C is negative, there's also a reflection. When C is positive, then it's just a stretching and or compression. And let me vary this. Let me control C from -2 to 2, just so we have a little bit more control. Create a smaller window of C, 0.01 step size, 0.1, there we go. Now clearly when C is 1, we have the exact same graph, because you multiply a function by 1, it doesn't change it. When C goes more than 1, we get the vertical stretching. When C goes less than 1, which stays positive, we get the vertical, let's zoom in here, we get the vertical compression. So there's the original, roughly, vertical stretching, vertical compression. And if C goes to 0, it flatlines it, because multiplying by 0 turns it into the 0 function. But once C goes negative, then we have reflections and compressions. -1 is just a reflection. Right, the two graphs are just reflections of each other across the x-axis. Hit the home button. But when C is negative but less than 1, we have a reflection followed by a compression. When C is less than -1, we have a reflection followed by a stretching. And if you want to do horizontal compressions, put the C inside there with the x. And now we've got, if C is negative, we had a reflection as well. So let's go C positive. When C is +1, there's no change. Once C goes more than 1, the reciprocal of C will be less than 1, so we'll get horizontal compressions. When C is between 0 and 1, will be horizontal stretchings. When C goes negative, then there's also a reflection as well as a horizontal compression stretching involved. When C is -1 specifically, let's get that to -1, then it's just a reflection only across the y-axis. But once C is negative and more than 1, then we have horizontal compression combined with a reflection. When C is between -1 and 0, we had a horizontal compression, or sorry, stretching combined with a reflection across the y-axis. So I encourage you to use the Desmos technology as you're working through this transformations to really work on building proper understandings regarding transformations and how to accomplish them.